Okay, hello everyone. My name is Megha, and today I'll be talking about our most tidal disruption events partial. This work was done with Professor Daniel Price, Alexander Higer, and Katie O'Shattle. So galactic center, most galactic centers have supermassive black holes at their centers, and this animation here shows the galactic center of Milky Way, surrounded by stars. And these stars can get close to the black hole and have interesting events such as tidal disruption events, which is what Fitz talked about earlier. These stars can directly plunge into the supermassive black hole, get captured, ejected, or have collisions with the surround neighboring stars. In today's talk, I'll be only focusing on the tidal disruption events as well. So in a TDE, a star gets close to the black hole and it's overcome by the gravitational forces of the black hole, resulting in material getting bound to it and eventually spilling onto the black hole. And the distance at which the gravitational forces of the supermassive black hole overcomes the self-interaction forces of the star is given by the tidal radius. And we saw it on earlier slides as well that we use beta parameter, which is the impact parameter. That is the ratio of the tidal radius to the pericenter distance to parameterize the strength of the encounter. So a larger beta parameter means a stronger encounter, while a lower beta value implies a weaker encounter because the pericenter distance is further from the black hole. So there can be two different outcomes when a TDE takes place. A star could be fully disrupted and fully destroyed, as was shown in this animation, or we can have partial TDEs where a star survives the encounter and goes on to live its life. Today, I'm going to only focus on partial TDEs in this talk. So the events have been observed before, as Fitz was talking about, and they have been they were theoretically we expect them to rise in X-rays, but they have been observed in UV optical as well. A few explanations are that there could be shocks taking place that peak in UV optical, or there would be a reprocessing layer, which reprocesses the X-rays, resulting in only UV and optical observations. Um, for X-rays, this plot here shows the black body radius. So what people do is they try to fit the light curves and get black body radii from the observations. And this plot shows the black body radii as a function of the black hole mass. What is interesting is that the uh, black body radius detect calculated for X-rays is close to the Schwarzschild radius, even though we expect that it should be close to the circularization radius, which is about two times the pericenter. So this is also a puzzle that needs to be understood. So in this work, we basically ran six simulations using Phantom, and we obtained our stellar model of a one solar mass middle-age main sequence star from Kepler, which is a stellar evolution code. Then we basically disrupted all these stars in Phantom, as you can see here. These simulations are shown only up to 4 days because after that, I use a sync particle to replace the star to speed up the calculations. And all these simulations result in star losing about less than 50% of its mass. So for beta zero point 0.6, it only loses about 1% of its mass, while for 1.6, it loses about 50%. So this shows a simulation, all the simulations run up to 95 days. So as you can see here, the material eventually starts falling back onto the black hole, and there is this formation of outflows that we saw earlier in Fitz's talk as well. So this basically is one of the explanation for UV optical, as I was talking about earlier. So we see that even partial TDEs are able to produce reprocessing layers. So this plot basically shows the mass accretion rate. So we expect that after TDE takes place, the bound material is on Keplerian orbits, and then it slowly starts coming back to the pericenter. So to determine how much material basically falls back towards the pericenter, we calculated the mass fallback rate shown on the left side. So we calculated any material that enters a distance of 1000 gm over c squared, and as part of the mass fallback rate. And we also did the calculation using the energy of the material using the Keplerian orbits. And we find that they match with the simulation calculation from 1000 gm over c squared radius. What's interesting is that for our simulations with beta value greater than zero point 0.8, the material can become has mass fallback rate greater than the Eddington limit, which is given by the dashed line here. Um, in TDEs, it was initially theorized that they would have a fallback rate of t to the minus 5 thirds, which was initially used for detections. And we see that for most of our TDEs simulations, they actually are more shallower than t to the minus, sorry, more steeper than t to the minus 5 thirds. So for to see how much material that actually falls back towards the pericenter actually ends inside the black hole, we also calculated the material that enters 6 gm over c squared, shown on the right hand side. As you can see, it's much lower than what we predicted from the mass fallback rate, showing that most of the material actually ends up in these reprocessing outflows that we saw in the simulations. So similar to what Fitz has been doing, we also performed light curve analysis and compared our simulation results with observations. So we obtained used data from these two papers, which contain full tidal disruption events, and we also considered Hinkle, which only contain partial tidal disruption events. So I should mention that Hinkle specifically only focuses on repeating partial TDE detections. So basically, a star comes back for another disruption with the black hole, and we plotted these data points on this plot. And then we calculated our simulation black body luminosity, radii, and temperature. And for all the beta values, we can see that our simulation values match with what has been observed for full TDEs as well as periodic tidal disruption events. We only show results for up to 100 days from our simulations, because we found that our simulations only converge up to that time. Um, and even our black body radii and temperatures are close to what has been detected so far. So far, all the simulation results that I showed here, they are for simulations where we assume that the energy is trapped. So shock heating is trapped in all of these simulations. But we found that this wouldn't actually be the case for low beta values, such as beta zero point 0.8 and zero point 0.6. So we also ran simulations where shock heating is radiated effectively. And this for our beta zero point 0.8 simulation. On the right-hand side, we show a plot where the disk basically forms around the black hole. So there's a black hole here at the center, and there's a disk formation around it. We can see that the maximum temperature lies around 10 to the 5 Kelvin, which is what we expect for soft X-rays. We again did light curve analysis on this simulation and found that the luminosities in X-rays would be about 10 to the 44 to 10 to the 45 ergs per second, which is what people usually detect for these X-ray TDEs. And our radii are actually close to the Schwarzschild radius, and definitely much smaller than the circularization radius. So kind of giving an explanation for what people have been detecting so far. And our temperatures, as I mentioned, are close to soft X-rays. So, in conclusion, stars can survive encounters with a black hole, and that's what a partial TD event is called. And our simulations match with what has been observed for full tidal disruption events and repeating partial tidal disruption events. Hence, we suggest that most observed partial TDEs might actually be partial. Thank you.
Questions? Yeah. Hello, thank you for the presentation. I was curious, you showed that the material falling at 6M, if I remember correctly, it was less with for higher impact parameter. So my question is actually about the outflows, not this. I was curious, okay, confused things. About the outflows, you mentioned that similarly, they also appear as full TDs and they reprocess the emission. I was curious if the outflows are stronger for higher impact parameters or less.
Yeah, there would be more, as you can see in the simulation. Um, yeah, so BR 1.6 is a stronger disruption event. So you see more material because there is just more material there to begin with. So there are more outflows as well.
Right. While in the lower impact parameters, this same material, which are not appearing outflows, it should be those that are accreted, right?
Yeah, so we do have material that accretes, yes. But again, material does form outflows in lower beta impact parameters as well.
Okay, thank you.
Any other questions? If not, let's